Fission versus fusion.
Now, fission is the process of splitting a very highly unstable isotope of a radioactive substance, and is a chain reaction. One of them splits up and causes multiple splits, releasing exponentially more energy. Now, even one of these will release a lot of energy.
Where against fusion is the colliding of two atoms in order to create a new element.
First off, we have nuclear fission, the bombs and the mishaps. Now, when someone thinks of nuclear fission, they think nuclear weapons, and when they think of that, they think weapons of mass destruction. Now, a weapon of mass destruction uses nuclear fission as a process of splitting a highly unstable isotope of a radioactive substance, and this releases a lot of energy. This is a chain reaction. One of them split up, and it causes multiple splits, releasing exponentially more energy. Now, chain reaction will only occur when critical mass is reached. Critical mass is required to sustain a constant reaction. If it's not achieved, if critical mass is not achieved, a lesser reaction will occur. Now, only certain isotopes of certain elements can sustain a long fission reaction, which is that big boom you want, which is uranium-235 and plutonium-239. Those are the two main elements, or two main isotopes used when building nuclear bombs. Now, the reason these two are used is because the nuclei release more neutrons when they break, increasing the chance to hit another uranium-239 or uranium-235 or plutonium-239 atom. Now, there are two recognizable major nuclear events, and those are the ones from Hiroshima and Nagasaki. Now, there's no such thing as a small nuclear weapon, because a small nuclear weapon is called a power plant, where the power is harvested to create energy, to create heat, to boil water, to send through pipes to spin turbines and stuff. Most people would expect a nuclear bomb to look like this. It's got the little circle thingy and the wingy thingy. No, that's not how it looks like. In reality, it looks a little bit more like this. It looks like a bullet. Now, this has three main components. It has the core fission where all the fission occurs. It has the nuclear fuel to power it, and it has the pellet of uranium that will be fired into the core to create this chain reaction. Now, other concepts have been tried in the past, such as this, as you can see in Fat Man and Little Boy. Now, this nuclear fallout of radioactive particles gets spread through a large area of land and is a very high mushroom cloud. And that mushroom cloud is affected by the wind that day. And that wind could go towards a very high population density, and it could even shut down entire countries if the fallout is high enough. Japan, 1945. Now, this had a very big effect in the Cold War, as well. This nukes now have the power to shut down entire countries. Basically, they have the power to turn countries into states of emergency, and that's why it was so big in the Cold War.
The reason I bring up nuclear weaponry is because it relates directly to our Canadian scientist Lewis Slotin. He was a physicist and a chemist. And to be brief about it, he was born in Manitoba, graduated university at the age of 23, and began to work at the University of Chicago, where he gained exposure to nuclear sciences, and he was invited to join the Manhattan Project in 1942. And he contributed to the development of the bomb by performing experiments with uranium and plutonium to determine their critical mass values. That's eventually how he died. He set off a small chain reaction and exposed himself to a lethal dose of radiation, and he died within 9 days of the exposure.
What is fusion? So fusion is the process in which two or more atoms, which are in extreme agitation, collide with one another in order to create a new form of element. Agitation is very important in the concept of fusion. This is simply because, as you may know, atoms are always in movement unless you're at or below 0 degrees Kelvin. So therefore, when atoms are heated, they tend to increase in motion, therefore they become more agitated. And in the process of fusion, the atoms must be at extreme agitation in order for them to blend together. You may be asking when this process ever happened inside the real life world. Well, let me tell you that without it, you'd most likely and will be dead. This is because the process of fusion, every single second, is occurring inside our sun. Now, our sun is 1.5 times 10 to the power of 7 degrees Celsius, which is 15 million degrees Celsius. It's very, very hot. Now, this causes any and all atoms to be in extreme agitation, which means that they are traveling at extreme speeds. Now, when these atoms do collide, this means that they're able to overcome the natural electrostatic repulsion between the positive charges of the nuclei and the negative charges surrounding it, meaning the electrons, and are able to fuse. The actual process of fusion inside our sun, there are two hydrogen atoms that collide to create one helium atom. Now, because of the law of conservation of mass, there are some protons and electrons that do end up escaping from this fusion reaction, and are released into the wild. So these protons and electrons that do escape carry energy, and we see this energy as heat and as light. Behind fusion. So we all know the formula E is equal to mc squared created by Einstein. E here is equal to energy. Energy is equal to m, which stands for mass, and c, which stands for the speed of light. But c is squared. Now mass in this equation is equal to the reactant mass minus the product mass. What this means is simply the mass of the reactant. So let's say in the example of the sun would be the mass of the two hydrogen atoms, compared to the product mass, which would be in the sun example the mass of the helium. So when those two are minus, you would put that into m, and you would just simply times that by c squared, which is the speed of light squared, and give you the amount of energy that fusion reaction has made. Let me begin by saying that there are no fusion power plants that are currently available in our world. But at the moment, there are many prototypes that exist and are being developed as I speak. I'm going to focus on one specific prototype called the Tomacaque that's being developed by ITER, which is a joint project that is currently based in France. Now they are developing a prototype that is using the same type of fusion reaction as in our sun. It's using two hydrogen ions, which are tritium and deuterium. So deuterium has one neutron and one proton, whilst tritium has two neutrons and one proton. The scientists at ITER have found out is that with these two ions, at the temperature of 1.5 times 10 to the power of 9 degrees Celsius, the energy that is created from the equation E is equal to mc squared is very greater than the energy created from our sun. This means at these temperatures, the electrons separate from the ions and it creates a plasma gas. And what plasma is a hot electrically charged gas that provides an environment in light elements can fuse together and yield energy. Once this reaction does occur, 80% of the energy created is transferred into escaping electrons from the deuterium and tritium fusion, and is absorbed into the wall of the reactor. So if you can imagine it, here would be the reactor, and here would be the walls of the reactors. As the electrons are going outside into the wall is absorbing the electrons as heat. So how does this heat transfer into electricity? That is very, very simple. Basically, once the reactor is cooled with, let's say, water, this heat transfers into steam, and this steam can be harnessed by using propellers and alternators to create electricity. Thank you for listening to our project on fission versus fusion, made by Kostya and Andrew.